Okay, so welcome to section 4.1, which is the graph of sine and cosine. And I might need to break this up into more videos because it's a very long section. So the graph of sine and cosine. Don't know if I should have pluralized graphs there, but you get the idea. We'll have two graphs, one for sine and one for cosine. So let's recall the unit circle. So recall the unit circle, which in math we annotate with S1. So the unit circle, it's always good to go over this multiple times until we get it. S1. So let's go ahead and try and make this large enough. We can have all of our everything. Let's see. So I'll make a small circle and then make it larger. So let me do this circle in. Okay. How does that look? Might need to make this guy a bit longer and maybe erase that guy. Okay, so there we go. That looks pretty good. Okay, so let's first look at our quadrantal angles. So let's look at the pi's, 0, pi, and 2 pi. So 0, pi, and then 2 pi if I go full circle. Okay, so those have coordinates 1, 0 on the unit circle and negative 1, 0 for these points here that are actually on the circle. So now let's look at the 30-degree reference angles. So let's see, maybe here. Hard to say where it should go. Maybe there. How does that look? Hopefully, nope, that does not look good enough. Okay, let's see if I can make this a bit better. Through the center. There we go. So we're 30-degree reference angles through the center. So the points that are 30 degrees from the x-axis, their coordinates have longer, so remember this is 1 pi over 6, 2, 3, 4, 5 pi over 6, 7 pi over 6, 8, 9, 10, 11 pi over 6, and then of course 12 pi over 6 would be 2 pi. Okay, so the coordinate there has longer x coordinate, so that's a root 3 over 2, and shorter y coordinate, the 1 over 2. Now we can think of 1 as a square root of 1 over 2, so hence it's smaller than the square root of 3. So in the second coordinate, our x, root 3 over 2 becomes negative, but the y remains 1/2. In quadrant 3, we have negative root 3 over 2 and negative 1/2, so they're both negative in quadrant 3. And then in quadrant 4, we have a positive root 3 over 2 for x. However, we have negative 1/2. So those are all similar, save for the SIG ends of each coordinate. So those are the, why is this not moving? Thank you, Apple. Okay, so now let's do our 45-degree reference angles. Let's use pink. Okay, so 45-degree reference angles along the main diagonal. Okay, so those are the pi over 4s. So pi over 4, 1 pi over 4, 2, 3 pi over 4, 4, 5 pi over 4, 6, 7 pi over 4, and then of course 8 pi over 4 would be 2 pi, and we'd be full circle. Now the pi over 4 or the 45s are nice because they're both root 2 over 2, root 2 over 2. So all I need to do is change the SIGN, so this will be minus for the x-coordinate in quadrant 2. And then both negative root 2's over 2's in quadrant 3. And then a positive root 2 over 2 for the x-coordinate in quadrant 4, but a negative root 2 over 2 for the y-coordinate. Okay, so now we have the 60-degree reference angles. It should be something like so. Remember, a reference angle is with respect to the x-axis, right? So how far away from the x-axis are we? We are 60 degrees in any quadrant. So 60 degrees are pi over 3 radians. So 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, and then of course 6 pi over 3 would be 2 pi, full circle. Okay, so at the 60-degree reference angles, our x-coordinate is the root 1 over 2, or 1/2, the smaller guy, and the y-coordinate will be the longer guy, root 3 over 2. So we have the same coordinates, save for SIGN in each quadrant. Okay, so in quadrant 2, they're both negative. And I want you to notice how the 30 degrees and the 60-degree reference angles, they swap their x and y coordinates, right? Because they're 30, 60, 90 right triangles. The other coordinate, of course, is 30 and 60. Okay, so last but not least, let's do our pi over 2's. So if we look at our pi over 2's, which are 90 degrees, to 3 pi over 2's, so that's 270 down there. The coordinate up here is 0 for x, 1 for y. The coordinate down here is 0 for x, negative 1 for y. So there we are, full circle, the unit circle. So hopefully everyone's getting a bit more comfortable with this. But what else do I want to recall? Let's recall for all points on the unit circle. So for all x comma y, for all upside down a, so for all x comma y, on the unit circle, I'm going to say element of S1. So that can be read aloud on the unit circle. Corresponding to theta, corresponding to theta, we have that x must be cosine of angle theta, and y is sine of the angle theta if we're on the unit circle. Let's also recall that negative angles, so negative angle measure, angle measure sweeps clockwise. So sweeps clockwise around the circle. So for example, let's go and look up here. Instead of, say, going to positive pi over 6, negative pi over 6 is the same as 11 pi over 6. So let me actually indicate that somehow. So 11 pi over 6, I just look up top. And what is the mirror across the x-axis? Well, the mirror across the x-axis tells me what it'll be. So this is the same as negative pi over 6 right here. And if I look at pi over 4, then 7 pi over 4 is the same as negative pi over 4, because that's the mirror if I look at it across the x-axis. These are mirror images. So I can see what my negative angle will be by looking at the mirror. So 5 pi over 3, that's a mirror of pi over 3, so that's negative pi over 3, etc. 3 pi over 2, well, that'd be negative pi over 2. because I look at the mirror right across the x-axis. 4 pi over 3, we'll look at that. That's a mirror to 2 pi over 3, so I claim that this is negative 2 pi over 3. Then 5 pi over 4 in pink here. That's a mirror to 3 pi over 4 in pink, so this is negative 3 pi over 4. If I look at the mirror image across the x-axis. Similarly, this 7 pi over 6 is a mirror to 5 pi over 6, so this is negative 5 pi over 6. And pi and negative pi are mirrors of one another, so this is the same as negative pi. So pi is the same as negative pi, which is interesting. Okay, so let's consider then things, or maybe I should, no, let's note. I'll call it a note, because I have too much orange here, so note. Let's do a chart here. Let's do theta versus cosine of theta, sine of theta, of specific angles. Let's see, what do I want to do? Let's do sine of theta. Yeah, sure. I guess it doesn't really matter. Let's do sine of theta. And then cosine of theta. Do I have enough room there? Okay, so what I'd like to do is various angles. So let's see. Let's start with, one. I guess I'll give myself 2 spaces for each angle I want to do. And you'll see why in a moment. Hopefully I'll have enough room here. I'd like to look at the x and the y coordinates for a whole bunch of angles. And then I'll never do it again because it's so cumbersome. But I think we should at least see it once, so you get the idea of where I'm getting all this from. And it's kind of like a nice meditative practice. Okay, so let's start with negative angles. Let's start with negative pi, which is the same as positive pi. But so let's start with negative pi, then let's do negative 5 pi over 6, the next one. So negative 5 pi over 6. Then let's do negative 3 pi over 4. So negative 3 pi over 4. Then the next one was negative 2 pi over 3. So negative 2 pi over 3. Then we had negative pi over 2. Okay, so negative pi over 2. Then we had negative pi over 3. Then we had negative pi over 4. Then we had negative pi over 6. And then we had 0. Okay, now we could do the positive guys. So positive pi over 6, I can just look at what I have here. So pi over 6, positive pi over 4. Do I have enough room? Oh boy, I don't know if I do have enough room. If not, I'll have to squeeze this in. Well, let's see what we have. Positive pi over 3, positive pi over 2, positive 2 pi over 3, positive 3 pi over 4, positive 5 pi over 6. Yep, I want to put one more, so what I'm going to do, I'm going to make these a little bit smaller over here, the sine and the cosine. I'll draw them a bit smaller, and I'm going to move everything over just one block so I can fit one more in here. Okay, so let me erase these. Okay, so I'd like to fit one more entry here. And of course that would be positive pi. Okay, so I'm going to fit positive pi here. So notice I've gone full circle from negative pi all the way around to positive pi. Okay, that's why I'm never going to do this again after this, because I think this will suffice. So first we have sine. Let me zoom in here. Sine of theta. Maybe that's too small. Sine of theta. Then in the second place we'll have cosine of theta. Okay, so let's look at this. Let's look at the coordinate at negative pi. So it's the same as positive pi, which is -1 for cosine and 0 for sine. So this is 0, comma, -1. Or -1, comma, 0, actually. I'm doing the y coordinate first. Doesn't really matter. Okay, so at -5 pi over 6, my y coordinate is -1/2. And my x coordinate is -√3 over 2. Then let's look at -3 pi over 4. Well, they're both negative and they're both √2 over 2. So -√2 over 2, -√2 over 2. Then we'll look at -2 pi over 3. So we have -√3 over 2 for the y coordinate and -1/2 for the x. Then at -pi over 2, we have -1 for the y and 0 for the x. At -pi over 3, we have -√3 over 2 for the y, but +1/2 for the x. Then at -pi over 4, we have -√2 over 2 for the y and +√2 over 2 for the x. At -pi over 6, we have -1/2 for the y, but +√3 over 2 for the x. Now finally at 0 or 2 pi radians, we have 0 for the y and 1 for the x. Guess if I was thinking, I probably should have done x first, but it doesn't matter. Pi over 6, we have √3 and 1/2, so for us that's 1/2, and √3 over 2 for the x coordinate. So for pi over 4, they're both the same, they're both √2 over 2. For pi over 3, or the 60-degree angle, I know that the y coordinate is bigger, √3 over 2, and the x coordinate is smaller, 1/2. At pi over 2, the y coordinate is 1, the x coordinate is 0. At 2 pi over 3, or 120 degrees, the y coordinate is √3 over 2, but the x coordinate is -1/2. At 3 pi over 4, the y coordinate is √2 over 2, the x coordinate is -√2 over 2. And at 5 pi over 6, which has a 30-degree reference angle in quadrant 2, my y coordinate is the smaller guy 1/2, but my x coordinate is -√3 over 2. Finally, going full circle, pi is the same as -pi. My y coordinate is 0. My x coordinate is -1. Now this is a lot to look at, so let's note what I'm going to do. So note, so when plotting sine and cosine, we are only going to use the quadrantal values. Quadrantal coordinates. Now, other instructors might have you use all of these coordinates. I am just going to use the quadrantal coordinates, meaning on the x and y axis. So at negative pi, at negative pi over 2, at 0, at positive pi over 2, and at positive pi. So those are the only ones I'm going to consider because they're easy. They're zeros and ones. Those I can handle. And then we'll fill in the rest. Okay. So note the domain for sine of theta and cosine of theta is theta in radians. So the domain is the horizontal axis. So for example, if I ask you to plot, let's say f of theta is sine of theta. Now I knew I wanted to plot sine first, which is why I put him first. So what I'm going to do is I'm now going to have two axes. So I have one vertical axis, which I'll call the f of theta axis. But then I've got a horizontal axis. And why do I always do this? Okay, the horizontal axis is going to be much longer. And it's going to be theta. So my domain, which used to be x values, is now theta in radians. And what I'm going to do, I'm going to do 1, 2, 3, 4 tick marks to the right, and 1, 2, 3, 4 tick marks to the left. And I want these to be quadrantal. So what I'm going to do is I'm going to say, okay, here's 0, here's pi over 2, meaning 90 degrees, here's pi, here's 3 pi over 2, meaning 270, and here's full circle, 2 pi, in the positive direction. Now, negative angles, which we know measure in the clockwise direction, I'm just going to put the same angle measures, but negative going to the left. And since this is a unit circle, I know that my radius is at most 1, right? Okay, so let's look at sine of theta. So at 0, sine is 0. So I've got the point 0, 0. At pi over 2, sine had a value of 1. So I go to the right pi over 2 and up to 1. At pi, sine had a value of 0 again. Okay. But let's go backwards. At negative pi over 2, sine had a value of negative 1. Okay. But then at pi, negative pi, sine had a value of 0. So what I get then is a nice sinusoidal graph, meaning actually a very sinuous, lovely graph, if I can draw it. Let's see if I can draw it. And we call this a sinusoidal graph. And this is one full cycle. But this goes on forever. So I could continue with this full cycle, starting again here at negative pi and continuing the cycle. So it would go to negative 1, back to 0. If I were to repeat, tack on, this will go on forever and ever. Amen. Or I could start over here, going to the left in the same manner. So it keeps on going up and down and up and down and up and down. Okay, so there we are. This is the graph of sine. But we plotted this between negative pi and pi in particular. So if I look at negative pi and pi, that gave me a full cycle, right? Between negative pi And positive pi was one full cycle for sine. It had one trough and one peak. Okay, but notice that this repeats, right? So let's notice this. So if I look from peak to peak, it repeats. But what is the distance between peak to peak? Well, if I have a distance to the left of 3 pi over 2, to which I add pi over 2 to the right, so that's 4 pi over 2, so that's a distance of 2 pi, which is a full revolution. That's interesting. Okay, so this, let me make sure we write that this was f of theta is equal to sine of theta. And the domain of this function, what color should I use for the domain? So the domain of this function was theta, right? So that's the horizontal axis, which is all real numbers, otherwise known as minus infinite to infinite. However, the range, if I look at the range of this function, what color shall I use for the range? Let's use orange. Notice that the highest value we get is 1 on the vertical axis. So the range has a highest value of 1 and a smallest value of -1. So the range is between -1 inclusive and +1 inclusive. So I go from +1 to -1. Those are all possible y values. And I go up and down between -1 and +1. However, the horizontal or theta values can be anything. They can go on forever and ever. Remember, we said that in radians are real numbers. Okay, so let's also note something about this graph. So note, where shall I put this? I guess down here. So note, sine is actually an odd function because it has 180-degree rotational symmetry. If I were to rotate this 180 degrees, this whole graph, I'd get the same graph. So sine of theta is an odd function. Odd function. That is, i.e., it has origin or 180-degree rotational symmetry. And what does that mean as far as the function is concerned? That means that sine of a negative angle is negative sine of its corresponding positive. Well, is that true? So sine of -pi is -1. Sine of positive pi is +1. Now if I tack on a negative, yes, that is true. So I can just tack on a negative to the positive value. That's what rotational or 180-degree functions satisfy. Now let's look at cosine. So for example, let's plot the function f of theta is equal to cosine of theta. So now I'm going to use the same type of a graph, very horizontally aligned, but now I'm going to use all of these values, the cosine values that I had. Okay, so let's go ahead. Theta versus f of theta coordinate axes. See if I need to. So theta is the horizontal axis. F of theta will be the vertical axis, and I will do 1, 2, 3, 4 quadrants to the right, 1, 2, 3, 4 quadrants to the left. So I start at 0, then pi over 2 for 90 degrees, pi for 180, 3 pi over 2 for 270, and 2 pi for a full revolution. And going backwards, the same things with negatives attached. Negative 3 pi over 2, negative 2 pi. And I know that I will get to 1 and negative 1, so let's do 1 and negative 1. Okay, so now let's look at cosine. And I guess in blue again. So cosine of 0 is, no, that's cosine of pi. Where's 0? Cosine of 0 is 1. So cosine of 0 is 1, so I'm up here at 1. Cosine at pi over 2, 90 degrees, is 0. Cosine at pi is negative 1. Now let's go backwards. Cosine at negative pi over 2 is 0. And cosine at negative pi is negative 1. So once again, I'm going to have this lovely sinusoidal sinuous graph to represent cosine. But much like sine, this graph doesn't stop. It continues to go on. So if I put another one of these guys right next to himself, it'll just repeat forever and ever. It'll just keep on going, either to the right or to the left, in the same manner forever. Actually, this part does not look that great. Let me draw that a bit better. A little more curvy, not so sharp. Okay, so there we are. So this is the graph of, did I write f of theta? Yeah, I did. So let's write it here. F of theta is equal to cosine of theta. But maybe I'll put that, no, I'll leave it there. So let's look at the distance between these two peaks here. How far away is it before it repeats? Well, the distance is to the left 2 pi units, so 2 pi, full circle to repeat, to get to 2 peaks, right? Okay, so let's note, what is the domain here? The values for theta. So the domain, the values that I can plug in for theta, is all real numbers. It goes on between minus infinity and infinity. I can plug in any value I want. However, the range, once again, the range is bound between positive 1 and negative 1 for the vertical axis. I can't dip beneath negative 1 nor above positive 1. However, the symmetry is not the same. Do you agree that there's no rotational symmetry here? However, there is a mirror image on either side of the y-axis. If I look at the y-axis as a mirror, so that's called even functions. So note that cosine of theta is an even function. So cosine of theta is an even function. As it's a mirror image, across the line or across the y-axis. So what this means is that cosine of a negative angle theta will be the same as cosine of a positive angle theta. Well, let's see. What is cosine of negative pi? It's negative 1. And positive pi is also negative 1. What is cosine of negative 2 pi? It's 1. What's cosine of positive 2 pi? It's also 1. So cosine of the negative angle is the same as cosine of the positive angle. That's what it means to be an even function. So I also want to bring back up the fact that, note, so the distance between two troughs, So the distance between two peaks, so like from here to here, like I have here, from here to here, peak to peak, or two troughs. Two troughs. So what do I mean by that? That would be trough to trough down here, or trough to trough down here, for both sine and cosine. So for both sine and cosine, is termed the period. So if we look above, the period, or the distance between two peaks, for cosine is 2 pi, and the period, that is the distance between two peaks or two troughs, for sine is also 2 pi. So let's formally define the period. So definition, maybe I'll do that. Yeah, I'll leave it in light blue. So definition. So a function f of theta, so a function f of theta is periodic. So that's what we're defining, periodicity. So is periodic if there exists a real number p. So notice what I say versus what I write. If there exists a real number p. So backwards E means there exists. P is an element of the real numbers. Oops, what just happened there? Thank you, Tim Cook. Okay, let me rewrite this because Apple. So if there exists P, an element of the real numbers, which I read aloud, if there exists a real number P, such that, which is backwards C with a line through it and a colon, so such that f of the quantity theta plus P is equivalent to f of P, or sorry, f of theta. So if these are true, then f is periodic. So, and P is the period. So that's what we mean by the period. And you agree that in this case, f of 0 is the same as f of 0 plus 2 pi. So the period there is 2 pi, because if I add the period 2 pi, I get the same value. So that's what we mean by the periodicity. Okay, so let's see how much more I should do. I think I'll do one more page before I break this up into separate videos. Okay, so let's recall. Because this section is fairly large, I want to have a couple of videos for this one. So for all angles theta, let me write. For all angles theta who in absolute value measure greater than 360 degrees, this implies we can write theta as some angle phi plus or minus 360 degrees times k, where k is some integer and phi is between 0 and 2 pi. So we've done this a few times, so hopefully this is making sense by now. And we'll reiterate. So note the period for sine theta and cosine theta is P equals to 2 pi, i.e. That is, it est, i.e. full circle. So you need to go full circle to repeat the periods for sine and cosine. So let's do some recap of what we've done in previous chapters. So for example, so let's evaluate the following. Wait, the following. So this is a recap. See if you remember these. Following, if I can spell it. Following. Okay. So number one, let's say we have sine of, how about 11 pi over 4? Okay, so in this case, theta is 11 pi over 4. And I know that 8 pi over 4 is 2 pi. So I claim that this can be written as 3 pi over 4 plus 8 pi over 4, otherwise known as 3 pi over 4 plus 2 pi. Okay, so this implies that sine of 11 pi over 4 is equal to sine of 3 pi over 4 plus 2 pi, which has the same value, so is equivalent to, what am I going to ignore? I'm going to ignore the 2 pi, right? So I claim that this is equivalent to sine of 3 pi over 4. So on the unit circle, that, of course, is a 45-degree reference angle in quadrant 2. Sine is a y-coordinate, so it's root 2 over 2. Okay, so hopefully that makes sense. And just in case you don't remember, 3 pi over 4, the y-coordinate is root 2 over 2. And sine is a y-coordinate, so number 2. Let's say we have sine of negative 8 pi over 3. Okay, so in this case, theta is negative 8 pi over 3. So what I'm going to do is I'm going to write this as 2 pi over 3, pardon me, from which I would have to subtract, actually, counting not my strong suit. Let me write this as 4 pi over 3. And what would I have to subtract to get to negative 8 pi over 3 from 4 pi over 3? Why am I writing this as a negative? Do as I say, not as I do. So I would have to subtract 12, right? 12 pi over 3. And the reason I'm doing that, 4 pi over 3, because 3 goes into 12 4 times, right? So I claim that this is minus a 4 pi, which is 2 revolutions, agreed? So hence sine of a negative 8 pi over 3 will be sine of a positive 4 pi over 3, which I'm going to subtract 2 pi, and I'm going to subtract 2 pi. So I can ignore each of those full revolutions, and this will be equivalent to sine of positive 4 pi over 3. So 4 pi over 3, where is 4 pi over 3? 4 pi over 3. Here it is. So I'm in quadrant 3, and sine is the y-coordinate, so that's negative root 3 over 2. Okay, so that will be negative root 3 over 2. Okay, let's do a couple cosine. So number 3. Actually, maybe I could skip a step, I don't know. Okay, so let's say we have cosine of 41 pi over 6. 41 pi over 6. So in this case, we have theta is 41 pi over 6. Okay. That's almost 42, so 6 would almost go in 7 times. But what I'm going to write this as is 5 pi over 6 plus, well, if I subtract 5, do you agree that'd be 36 pi over 6? Okay, so that's 5 pi over 6. How many times does 6 go into 36? Well, 6 times, right? So that's 3 full revolutions. So I claim that cosine of 41 pi over 6 is really cosine of the quantity 5 pi over 6 plus, well, 6 pi is really 2 pi plus 2 pi plus 2 pi, right? So I've gone full circle 3 times beyond 5 pi over 6. So this is just going to be equivalent to cosine of 5 pi over 6. So cosine of 5 pi over 6, that's the 30-degree reference angle in quadrant 2. So let's look at that. So the 30-degree reference angle in quadrant 2, cosine is the x-coordinate, so negative root 3 over 2. So negative root 3 over 2. And now let's do one more for good measure, and I will stop this portion of this section at this point. So let's evaluate cosine of, let's do a negative 7 pi over 2. So in this case, we have that our angle theta is negative 7 pi over 2, but I'd like to have a positive number here. So I claim that this is pi over 2 minus 8 pi over 2. So that is, this is pi over 2 minus 4 pi, which is 2 revolutions. So cosine, why am I having so much trouble writing the word cos? So cosine of negative 7 pi over 2, I claim that this is really cosine of pi over 2, from which I'm subtracting 2 revolutions. So minus 2 pi minus 2 pi. And I know that if I've gone full circle, this will be just equivalent to cosine of pi over 2, which is the x-coordinate at 90 degrees. So I claim all of this is for nothing, or at least for 0. Okay, so I'm going to stop it here, and we'll start plotting more difficult things in the next video.